welcome to Module 53, extending the last module on attention mechanisms. Now we put them into what are called transformers in both encoder and decoder architectures. By the end of this module, you should be able to explain why a single attention head, like we talked about in the previous module, is limited and how multi-head attention addresses that limitation. You'll be able to describe the role of positional encoding and distinguish sinusoidal from learned variants. At least you'll know that there's a difference. You'll be able to identify sublayers in a transformer encoder block and a transformer decoder block. You'll be able to compare or at least know that there's a difference between encoder-only, decoder-only, and encoder-decoder transformer variants. And you'll be able to implement a small transformer encoder in PyTorch and implement its behavior in one sequence task. I should note that these are the three main components of today's module: multi-head attention, positional encoding, and encoder-decoder blocks. So, in Module 52, we had this core mechanism which we call attention, which others call attention also, and which has a couple of components to it. The first of which might be that we have these vectors, Q, K, and V, for query, key, and value. And these basically represent a required information at a particular point in time, which is the query vector, a key vector, which tells us which of the available points in context contains information that's relevant to us now. This is basically a dot product between the keys and the queries. And then V is the actual information at those positions marked by the keys. So we have a degree of relevance. We combine those degrees of relevance in a softmax function, which basically normalizes them and turns them into a pseudo probability. And then that basically tells us how much information from each of these contextual vectors we want to incorporate in the current moment in time. What's shown here is representing these vectors, Q, K, and V, in terms of matrices. We have T is the total number of elements we have in our context window. These could be like big T words. D sub K represents sort of the dimensionality of our key vectors. D sub V is our dimensionality of the information vector. So in this representation from last time, we basically showed that, well, recurrent neural networks, if you want to move information from one point in time to another, you have to kind of push it through a lot of matrix operations through multiple moments in time, but attention mechanisms are kind of like shortcuts through the entire sequence. So you can get positions that interact in constant time. So far, we only had one layer of attention mechanisms. So we had, one piece of input, X, and then we had our representations, and then we had the attention mechanism on top of it. As we're going to see today, this is something that's stackable, just like every other component we've seen so far in our neural networks, which is one of the benefits of neural networks. We talked a little bit about how attention weights are interpretable as sort of diagnostics. We can look at these matrices of heat maps that show like what moments in time are attending to other moments in time, so to speak. And sometimes this can be very useful. In some of our examples, we showed how this kind of aligns with our expectations, but we cautioned that this is not a causal explanation. Just because an attention weight happens to be strong doesn't necessarily mean there's a if-then causal explanation. Then we went from sort of cross-attention mechanisms from like encoders to decoders to self-attention. So given a particular sequence, we can use attention of a sequence on itself. We still had queries, key, and values, but instead of going from a target sequence to a source sequence, like trying to translate outputs and attending to the inputs in T and S respectively, we had a single sequence, and we wanted to represent that sequence very well. And then we talked a little bit about how this allows us to come up with embeddings for words that are not static. So whereas previous representations for words in, say, the word-to-vector glove models from several modules ago, there's a single vector which represented the word play. The word play could change based on the context in which it occurred. And that's also true of any other word in the sequence. So the open questions from last time that we didn't really answer is, well, if you have one set of queries, key, and values and their weights, and if this captures one particular relational pattern, so at this particular moment, what is useful for me right now? Usually what is useful has one particular meaning. But what if there's lots of different things going on in the same sentence and we need to attend in different ways to different parts in that sentence? So I'll not just have one attention over the words that are relevant to me right now, but according to this frame of mind, these words are important. According to that frame of mind, those words are important, etc. So we need to be able to solve that challenge. Self-attention mechanisms ignore order. And we mentioned this briefly last time also. In fact, we had to encode position in one of our worked examples just to get the entire system to work as expected. But we're going to see that. Self-attention doesn't really have a concept of order by itself. And we also just looked at one single layer of attention. But like so many other times in neural networks, we want to be able to compose these things on top of each other to represent different levels of architectural conceptual depth. So we're going to do those today in each of those three blocks I just mentioned a moment ago. So each of these questions has answers in our transformer architecture. So let's start with the first one, multi-head attention. So the scaled dot product we saw last time of keys and queries projects the input into this single query and key, and then therefore value space, and will compute one weighted combination given the softmax functions. But that means that there's one particular set of linear weights, and that determines which pairs of positions are related to one another. There's a strong degree of attention from right now to this particular other word. It also, therefore, immediately tells us how information from one position is going to be summarized in another, because we're going to weight the value vector from one position by an amount that's set once for that particular attention. But natural language in particular, which is an important area of AI generally, but for many other sequences also, there's lots of things going on at once. Like in any particular conversation, there might be the facts of the matter, there might be the nature of the conversation. So like the relationship between the speaker and the listener is sort of implicit in how the utterance is being made. There's the opinion of what's going on, like the subjective experience, which is also transported. There's other pragmatic things layered on top of it. So language is complicated, and having a single way to attend to the different words in the sentence and say this is important and that is not is extremely limiting. So for example, we have the sentence, the animal didn't cross the street because it was tired. This is a kind of a very simple sentence, but even in the sentence, there's a lot of different things going on. So you might care about what objects, what noun phrases, what entities in the sentence refer to the same entity, or how they stand in relation to one another. So in particular, I just want to highlight that it is like a pronoun, but what does it refer to? Does it refer to the street? Does it refer to an animal? I mean, cross can also be a noun, so maybe it refers to cross if you're not careful. I mean, it's a verb here, but you get the idea. So for a particular attention that wants to link together these entities, we call this a coreference link. Coreference was literally the first task I ever worked on as an AI researcher in my first year of an undergrad. Regardless, it refers to animal, and we want one attention mechanism to kind of draw a strong link between the position for animal and the position for it. Street and cross are also related. So there's a verb. The verb takes a object, in this case, which is the street. So we have to cross something. What is it that we cross? The thing that we cross is the street. They're semantically related. So we want, when looking at the word street, we want to refer it to the word cross and vice versa. And this is a slightly different kind of attention. So now we're not trying to link entities together that mean the exact same thing in the sentence. We're talking about now, like, how do these different words relate to each other syntactically. This is the verb, this is its object, or maybe this is the verb, this is its subject. Another form of attention might be negation. So we have this didn't, like the animal did not cross the street. This is a whole other topic of natural language processing. It may not be the deepest of topics, but it's relatively deep. Sometimes we need to change the semantics of parts of a sentence. How do we do that? Well, we have to pay attention to what is being negated and how often these negations kind of overlap with one another. Another grammatical rule, but this is slightly different than the other. So an attention mechanism that only knows how to relate verbs and their objects and their subjects wouldn't necessarily learn how to understand negations. So these are different dependencies that involve different kinds of attention. So trying to force this all into the same attention head might be overwhelming. So to put it this another way, a single attention head can learn one main pattern very well. At least that's what we're saying right now. And but if we want to capture several things at once, then we should have multiple heads. Instead of having one attention mechanism, we should have multiple running at the same time in parallel, and each of them are going to have their own learned projections and concatenate the results. I'm going to mention this again later, but I'm mentioning it now. These examples are contrived for the sake of trying to explain what's going on. It's not like, this is the specific head that only understands coreference resolution, and this is the other head that only understands verb-object agreement, and this is the only head that looks specifically at negation. So first of all, just like so many other things in machine learning, each of these components will usually understand a blend of different things. It's not just totally siloed in terms of their function. Second, because the nature of these heads are going to be learned kind of automatically from data, they don't necessarily learn categories of functionality that map cleanly with what our expectations are. So it's possible that a head will predominantly understand coreference. It's also possible that this function will be spread over multiple heads. It's also possible that this won't be learned at all, just because it didn't help the neural network achieve its empirical risk optimality. So this is just here just to kind of set the stage, but the reality is often a little bit more complicated than that. So the idea now is we're going to have a hyperparameter h, which is just the number of attention heads that we're going to run in parallel. Instead of having one, we'll have several of them. So for a particular head, we'll have an attention mechanism like we defined last time. This will have the query vector, the key vector, and the values vector just as before. And it'll have these weight matrices, which will be learned through backpropagation in a way that we're just glossing over in these slides. But it'll work very similar to how we looked at gradient-based backpropagation in previous modules. So each of these weight matrices will be indexed by their particular attention head. So there'll be one weight matrix for query vectors in attention head I. There'll be one weight matrix for keys in attention head I, and so on. So each of these will have the same dimensionality. They'll be basically D submodel, which is another hyperparameter, which essentially is replaces T. It's like the length of the sequence. So normally, just for tradition's sake, these are normally powers of 2. We'll talk about BERT a little bit later on. Traditionally, BERT had a window of 512 tokens it could read, or like positions it could read in a sequence. So D model is what we called T a moment ago. Sometimes we called it S for the source, but it's just basically a hyperparameter that describes the length of the window we can deal with at a time. And then D sub K and D sub V are the same dimensionality of the key vectors and the value vector respectively. Anyway, so we're going to have these weight matrices, which are basically the same size as before, but we're just going to have one for each of our heads that we have. And then we train them, we update them according to our backpropagation algorithm. And then we'll combine them together in what we call this multi-head component, which is the concatenation of all of these heads, again multiplied by yet another weight matrix, WO, which is the number of heads we have times the number of value vectors we have times the number of positions we have. The actual dimensionality of this is not going to be that important to you, but I'm just putting in here for completeness' sake. This is just basically a weight matrix that allows us to combine all of the heads together. So a typical implementation choice, I don't have a link here, but this comes up occasionally. It might just be a subjective anecdotal thing, but it's something I've noticed. The dimensionality of the key vectors is often said equal to be the dimensionality of the value vector, which is not often the hyperparameter d submodel divided by h. So if we had a single head, well, we have d submodel, but we have h heads, so we just split it up h ways. So the d sub k and d sub v will be these small fractions of d submodel controlled by the hyperparameter h. This is just a visual of what we've been talking about. This is from the famous paper, Attention is All You Need, which introduced a lot of these concepts. We have our values, key, and query vectors. We have our linear transformations, these W vectors we mentioned a moment ago. Here there's three of them, so H is 3, at least visually. So we'll have weight matrices for each of these heads, and then we do a scale dot product attention, we concatenate, and then we have a linear combination. This is WO, which we saw a moment ago. So, I mean, conceptually it's pretty straightforward. It's just a regular attention head, but now we have H of them. And then we combine them together with a concatenation. So why does this help? Well, there's empirical observations. So from that very same paper and then from some follow-up work, the different heads in large language models or other like pre-trained language models, which kind of predate so-called large language models, they do specialize. So they don't necessarily specialize in like as cleanly linguistic a way as the examples I showed you a moment ago with the animal crossing the street, but they do kind of specialize. They do perform different tasks. So like some of them might attend to nearby tokens, and therefore the idea is that they're probably attending to local syntax, like at the phrase level. Some of them track long-range coreference, so that's something that has been observed, and some of them attend to positionally adjacent tokens only. And like I mentioned a moment ago, no single head will do all of these very well simultaneously. Actually, it's not what I mentioned. What I mentioned a moment ago is that none of these H heads will do any of these uniquely. So often these functions are spread over a couple of heads. Maybe one of them is more predominant than others, so there is some specialization, but it's always a mix. What this last bullet point is saying is that if you have a single head and you have all of these linguistic functions that you're asking it to perform, it's going to struggle a little bit because you're training this one weight matrix for this one head. Well, it'll be 3 weight matrices, one for key values and queries. It'll not really learn all of these things at the same time, but rather kind of an average blend of everything, which is not as specialized. So from a somewhat more formal perspective, each of these heads will be a different linear projection, like we saw a moment ago, of the same input. So they'll project in different ways, and therefore the model can represent different subspaces. In the interaction substructure basically just means the way in which these tokens interact with one another, which is the thing we're trying to identify through these attention mechanisms. So concatenation will merge everything. So we're just kind of like I guess not even summing together. We're literally concatenating together the evidence together, and then we can apply this other weight matrix W sub WO to remix everything. So this is more important than that, or this is how you combine coreference with phrase structure. But they're still separate pieces of information that we're not kind of averaging out through a single linear transformation. So again, there's no silver bullets. Just because you use multi-head attention doesn't mean it's magic. Some heads in trained models can sometimes appear to be redundant, or at least very difficult to interpret. So if you look at these multiple heads that you've now integrated and look at their attention mechanisms and see what they're attending to, qualitatively, it can be very difficult to see what's going on. We're going to see an example, to be fair, in one of my worked examples that's hard to interpret. Sometimes they're redundant, which is much more easy to quantify. Like if these two heads are attending to basically the same thing, then you can compare their distributions, and therefore you can conclude that they're redundant. So just because they can specialize in unique and different ways doesn't mean they're going to. So what they end up learning is sometimes almost an accidental byproduct of the task, the model size, the data you happen to have, the random initialization of those matrices in the first place, and so on and so on and so on. So just because you have multiple heads doesn't mean you're automatically going to get all this wonderful functionality out of it that's unique and relevant and understandable. So sometimes if you're encountering the situation where multiple heads are attending to the same thing or in the same way, You can do head pruning. This is where you can remove some heads without significantly degrading performance. You can read about it in this paper. So, opening things up to provide extra headroom to learn more things, to have more capacity, like we talked about many times in much more or much less recent modules, is a good thing, but not all of it's always going to be used. And therefore, if you have highly capacious models, there's also the risk of overfitting, which is always an issue with very big, deep neural networks. So here's an anti-example. Why not just make d sub k larger? That's our dimensionality of the key vector. So the idea is this: if one head is limited, and if it can't learn the variety of relationships that multi-head attention can learn, well, why have all this extra complexity? Why not just make d sub k bigger so that it has more capacity? And we've seen lots of examples in the past of more capacious networks being able to learn more things simply by means of their capacity. To some extent, the double descent thing we saw earlier as an example of neural networks being able to overcome its limitations because of its sheer size and because of our patience in training it. So we say, well, bigger is better. We'll just make d sub k bigger, and it'll be able to learn all of these things that we are asking the multi-head attention to learn for us. This is not exactly the same. So if we increase d sub k in one head only, this will increase the dimension of every individual query, but the queries are still going to have to be compared to each of the keys that we have available to us in terms of the length of our token length, the window we have available to us. And then we're going to pass that through softmax. So we're going to compare keys and queries, and then this is going to be normalized through softmax. We're going to have a bunch of alphas, which is going to behave kind of like a pseudo probability over the positions of the tokens we have in our sequence. It's only going to do that once, right? So, even if a more capacious d sub k could, in theory, learn more things, it's still going to have to be collapsed over the single sequence once. And therefore, it's not going to be able to learn separable things. It's going to, in some sense, average everything together. So it's not going to be able to say, I'm going to give a certain amount of weight to position 3 in this circumstance, and I'm going to give it a different amount of weight to position 7 for a different circumstance, and pick and choose what functions I'm applying to each of my weight vectors. It's going to have one weight vector. It's going to have to do one thing only, one level of attention. So the best case scenario is it's going to average out all of the different functionality that it's meant to learn through its extra capacity, and sometimes when you average out a lot of different, very disparate things, you end up losing information, and that's kind of what would happen here. So that's a different kind of capacity, right? So even if you have technically the same number of parameters available to you, because you have to collapse everything once in a single head, you're only going to have one form of attention at the end. Whereas if you have multiple heads, every head can attend to a different thing. It can attend to different functions of the relationships between the tokens, if that makes sense. So that's a crucial thing. So doing things separately and then concatenating them together allows you to have distinct contributions instead of one big average contribution. So that wraps up the multi-head attention. So the purpose of multi-head attention is just basically to allow for the complexity of, in particular, language, but other sequences to be represented in multiple different ways instead of having to have one form of attention. Next, we have positional encoding. So in module 52, in the last module, we talked about self-attention, which is basically trying to represent a sequence on its own. And every output position would be obtained by comparing content through dot products between query and key vectors. So we'd have the alpha sub ij would basically tell us, if you're in position I, and you have all your other neighbors j, you have an attention weight obtained from softmax from position I to position j. So j is something you can pay more or less attention to according to the value of alpha. You multiply that weight by whatever vector is in that neighbor. So I need to pay a lot of attention to that particular word. I'll take a lot of its meaning, and then I'll just kind of collapse it into this sum over the weighted combinations of all of my other neighbors j. Alpha sub ij here is just a softmax function we saw previously, making some of the the sizes of these vectors explicit here, but that's you can ignore that for now. That's not the important part. The important part now is that if you look at this summation and this sum, just like you have a regular sum, you can just move the terms around in this sum, and you're going to get the same result. So the attention you're going to get from summing things in the completely reversed order or in some totally random order is going to be the same. In other words, you can shuffle the attention weights. If you shuffle the tokens around, then the weights are going to follow them, and you're still going to end up with the same overall contribution of the context. But everything will be out of order, and we won't know the difference. So that's what I was saying earlier when I was saying that attention mechanisms are order agnostic. There's nothing we've obtained so far that allows us to say this word occurs immediately before you, this word occurs in position J. There's nothing of the sort. So, in other words, a pure attention or self-attention layer will not be able to tell that this is the token at position 0 and this is the token at position 4 unless there's some label associated with each of those representations. And that's what we need this position encoding for. So here's an example. If you don't have this positional information, then you have a sentence like dog bites man and a sentence like man bites dog. And each of these sentences will give you the same kind of attention to the different components, the different tokens in these words. It'll obtain the exact same ones after one self-attention layer. And that doesn't make any sense here. Obviously, there's a big semantic difference between a dog biting a man and a man biting a dog. And that's just a simple 3-token sequence. So we're going to have to build in some kind of representation here of position. So this is maybe somewhat of a microscope thing, but I'm leaving it in just to make sure you get things at the high level. I'm not going to ask you to memorize these equations here, but I just want you to understand what's going on at a high level. So this original transformer paper that we keep coming back to adds this fixed positional encoding, or PE, which is appended to the input embeddings before any attention mechanism is applied to it. So you have positions, position 0, 1, 2, 3, all the way up to position t-1 for a sequence of length t. And you're going to have dimension 2i or 2i plus 1. The position encoding here at position pos, 2i will be sine or cos. These sines are cosines. I'll show you a visualization of this in a moment to explain why we're doing it this way. So why are we using sign and position? So first of all, if I wanted to say that this token comes at position 0, why don't I just have a vector with a bunch of zeros in it? And then for position 1, I could have 1 and then a bunch of zeros. And for position 2, 0, 1, a bunch of zeros. Position 3, 1, 1, a bunch of zeros. And you get the idea. Why don't I just count off the positions in terms of integers and then just represent their position in terms of integers? Or indeed, why don't I use one-hot encoding for the positions? So this is the vector for position 1, or 0, 1, 2, 3 will just be a 1 in the associated index. There's a couple of things here. So the first one is that, we want every position to be a unique vector. We actually get that if we were to use a position vector for just using integer indices or one-hot encodings. A bit more of a challenge is that nearby positions will have similar encodings. So if you go from position 15 to 16, you'll have a bunch of 1s and a 0, and then the next vector will be a bunch of zeros and then a 1 and then a bunch of zeros. So those two encodings will be just very different from one another in space. Similarly, the one-hot encoding vector, every possible number will be completely orthogonal to every other possible number, so there won't be any kind of measure of similarity between 15 and 16. 15 and 16 will appear as far apart as 15 and 15,000 if you have a transformer that has that kind of capacity. So right off the bat, using integer encodings and one-hot encodings sort of breaks the idea that nearby positions will have similar encodings, which we want. We want words that are close to each other to appear close to each other in terms of these encodings. So if we use these sine waves and the sinusoids, then encodings at different dimensions will oscillate at different frequencies. So I'll show you what that means in a moment. these I vectors. These aren't I vectors. I vectors is a completely different thing, but we'll see in a moment. The dimensionalities will provide different sine waves oscillating at different frequencies, and this will basically give us a ruler that lets us measure how far apart these positional encodings are. And the encoding is deterministic, so we're not going to have to learn anything about the positions. There are learned forms of position encodings, which I'll mention briefly later, but this is deterministic and completely, it's very easy to obtain these position encodings. This actually helps us, the reason I mentioned that is it helps us to generalize to unseen sequence lengths. So if you learn a position encoding and you only have data that's only 10 words long, and you use this positional encoding, and then suddenly you start seeing sequences that are hundreds of tokens long, this positional encoding will still work and it'll still generalize to sequence lengths that you've never seen before. And again, generalization is very important in machine learning. This is the visualization I was talking about before. So this this graph over here basically shows the sine waves we saw in the previous slide. I don't want to go too deep into it because this week we spent a lot of time just trying to get you the intuition here. The intuition of why this works is not just important. It's not as important as the mere fact that it works. So you have these different positions down here. These represent the different like words in your sequence or elements of your sequence. These sine waves, we have the dimensions that we talked about a moment ago, the i's. The dimension 0 has a high frequency. This is the purple curve. 8 is somewhat lower frequency, this blue curve. 32 is this relatively low frequency wave, this green curve. And then dimension 60 is a very low frequency sine wave, with this red curve over here. So we can look at the sine wave, which is basically representing our positions. And we can look at any one of these positions and look at the values of these sine waves that are kind of overlapping each other at the same time. And then we can look over here on the left, and this is sort of a top-down view of the values. Here we again have the position index of the tokens. So this is the first word in the sequence, the second, the third, the fourth, all the way to the end of this sequence. We're encoding sequences of length approximately 52 or so. And then you have the encoding dimension. Basically, how many of these sine waves do we have available to us? And that's the y-axis here. So the values here basically represent the redness and the blueness in this graph basically represents the amplitude of the sine wave at that particular position, which I mentioned a moment ago. You can have position 10, and you can look over here. Dimension 8 in this blue curve is about minus 0.6. So hopefully here, dimension, I can't really tell here, 9, 10, 8, here it is. This blue dot over here represents that blue curve over there. That's a bit bluish. It's in the negative territory anyways. This is really not important. I'm getting kind of into a rut. Jumping out of here, you look at each of these columns. Each of these columns will be totally unique. You can see kind of this pattern is kind of evolving over time uniquely. No two columns in this matrix on the left will be unique, so there is like a uniqueness constraint is satisfied across the columns. Every position gets a unique index. Also, nearby vectors will appear very similar to one another. So if you look at any pair of columns here, these vectors, these position encodings that are close to each other in terms of the token index, in terms of time, like these two words are close to each other in a sentence, the encodings are also going to be similar to each other in the position encoding space. If you don't believe me, I'll show you a visualization of that in a few moments also. Okay, so this is really getting a bit more detailed than I was hoping to. You're not going to have to memorize the sine and cosine functions over here, but as big picture, you know that these sine and cosines produce these sort of maps that allow us to get position encoding. So each of these columns are going to be vectors that we are going to concatenate to our input tokens, and that concatenation is going to be the input to our sequences and our attention mechanisms and so on. So this is certainly a side note. Why are we doing position encoding? What does it actually get us? Well, once we add position encoding to the token embeddings, like I just mentioned a moment ago, the model will receive the content of the token. So what does the word actually mean? But it'll also get where it sits in the sequence, so it'll know which words are close or far from each other. So now these weights that are learning what to attend to will implicitly incorporate positional information via these query key dot products. So if I'm at a particular position and I'm trying to figure out what to pay attention to, I can do so by also being sensitive to where the position is relative to where I am currently, because of the similarity of the vectors, those columns in the matrix I showed you a moment ago. Yeah, relative position can be captured. This is a bit more detail, but the relative position is this dot product between the positional encoding at position pos and the positional encoding at position pos plus k or minus k. So only based on the offset, the sinusoidal encodings will give me the relative position. I'm going to show you an example of this in a few moments, or an example of the consequence of this in a few moments. There's a alternative. So I like this because it's beautiful and very insightful. Like the people who discovered this, it took a rare moment of insight that doesn't happen too often. But you can also learn these embeddings. So the people who want to learn everything and not have any human involvement whatsoever say, well, you can have you can have the token representation at every moment in time. You can have the position encoding for every moment in time, and you can learn that position encoding up to a fixed length. So BERT is one of the original representations of text using transformers. This is from another very famous paper in NACL. This paper, you should read it. I should have a link there too, but you can find it. It's a very important early paper with some problems with it, but that's another story. It had a very fixed length famously, so it was extremely powerful at the time for understanding sequences up to length 512, but if you have a length of text that was 513 or more tokens in length, a BERT simply could not be used because it learned its positional embeddings automatically from data. So a bit of a trade-off there. So just a quick comparison. This is something that's maybe a bit less, and as an aside, I want you to understand that you can do sinusoidal and learned positional encodings, but the details of their trade-offs might be less important. But I'm mentioning that now. So in sinusoidal positional encodings, you don't need extra parameters. Sorry, you do. But you don't need those with learned positional encodings. Sinusoidal encodings generalize beyond training length, like I mentioned a moment ago, but that's not the case for learned encodings. The learned positional encodings actually adapts to the data distribution. So, it's going to be the case that some words just occur naturally at different positions in sentences. Like who, what, when, where, why questions might occur very often, or words might occur often at the beginning of sentences compared to in the middle. Who knows? But the data will tell us, and learning positional embeddings gives you that information. So Vaswani et al. Introduced the sinusoidal embeddings we talked about a moment ago, BERT, and then later on GPT, which you might have heard of, also learned their embeddings for position. In practice, both will perform similarly on benchmarks. For a very long time, there seemed to be no difference between the performance of BERT and GPT. Actually, the side note I wanted to mention a moment ago, there was another form of recurrent neural network called ELMO, which was the precursor to BERT. And BERT came on the scene with transformers, and everyone was very excited about all their benefits. And to be fair, transformers are exciting, and they do provide a lot of benefits. But in hindsight, there's a recent research that suggested that actually the early work in BERT and GPT failed to do the science properly and might have made some conclusions somewhat hastily. Regardless, around 2019, 2020, and even 2021, BERT and GPT were still sort of neck and neck in the community. Regardless, the third of the three main components I wanted to mention was encoder and decoder blocks. So a single transformer encoder block will have usually two sublayers, followed by a residual connection and a layer normalization. So there'll be X, there'll be multi-head attention on X, and this will be passed through a layer norm, and this will be a sublayer 1. Then sublayer 1 will be combined with a feedforward network that takes as input sublayer 1, and then is passed through a layer norm. This is the residual connection I mentioned a moment ago. So sublayer 1 can pass through a FFN this way and pass in straight ahead through a residual connection to a layer norm, and all of that forms sublayer 2. I'll show this visually in a moment in case that's not clear. The position-wise feedforward network. For now, you can just picture it as a regular feedforward network. This is the ReLU function. This is the max of 0 and the linear combination of its input z times the weight matrix plus its bias. All of this multiplied by a weight matrix plus a bias. So lots of these good old linear transformations where weight matrices and biases are learned functions, as always. Each of these will have are just real valued numbers that are learnable parameters that have appropriately sized dimensions, which sometimes are left as a hyperparameter. Yeah, so this FFN is going to be applied independently at every position. So every position, the sublayers will be, sublayer 1 will be passed through an FFN, and then an FFN will kind of learn how to represent the particular token at the particular time, given the multi-head attention from sublayer 1. Having these two sublayers allows you to have two different roles. So the self-attention mechanism will mix information across the positions, like we talked about earlier. Every token will collect context from the rest of the sequence, and this will all be combined. In particular, the FFN transform will combine it independently for this particular position. So essentially, this FFN will be like the same kind of nonlinear function, but it'll be applied differently to every particular position that it's used in. So we know about residual connections to some extent. We saw in module 34 that deep neural networks are prone to vanishing gradients, and we're starting to add lots of weight matrices being passed through other weight matrices over and over again. So therefore, the problem of vanishing gradients becomes a bit of a risk. So one way around that is to have these residual connections. So we have this layer norm that has x, which is our sublayer 1, plus f of sublayer 1, which is the FFN. We talked about a moment ago, the feedforward network. Pass through another layer norm is a form of doing these residual connections. This will allow gradients to pass directly back from the output of these encoder blocks back through sublayer 1 directly. And this allows you to, even if you have many of these encoder blocks on top of each other, a lot of these early transformer networks had dozens and dozens of these layers. So these residual connections allow us to push gradients back more effectively. Transformers use layer normalization within each of these blocks. Why are we doing that as opposed to batch normalization? So just to remind you, we talked about this earlier, layer normalization normalizes across feature dimensions for every token independently. The math here doesn't matter so much, but we talked about that a bit earlier. This basically keeps things normalized at the level of the layer. Whereas like the batch size, can change. It's a hyperparameter that is used mostly to control the speed and the general behavior of training. So what we want now is not something that's necessarily based on the mechanics or dynamics of training. We want to normalize based on the representations that we're learning. So layer norm is useful for controlling for like spikes in the representations in the representation dimensions. So batch norm and layer norm, even though they're both part of the norm family, are solving kind of different tasks, and layer normalization is what's important now when we're trying to control representations. So we have the encoder block, which I'll show you a visual of in a moment. Then we have the decoder block. The decoder block has 3 sublayers. And each of them has these add and norm components to them. So there's a masked self-attention. So we talked about self-attention quite a lot. We'll talk about masking in a few moments because we haven't talked about that before. But basically the idea here is that when we're decoding, we're only going to attend to tokens that occurred before us. So we're going to kind of mask everything that we haven't seen yet in the future, which like technically we would be able to see, but we shouldn't be able to see because those words haven't been uttered yet. So we'll attend only to things in the past through this mask. And we'll do so in our own sequence because we're doing self-attention, because we're representing the decoding that we're doing. There's still a cross-attention, so we have an encoder and a decoder. We have inputs and outputs. Maybe we're translating from English to French or French to English or something. So we still have an encoder on our inputs, and we're still decoding on our outputs. So when we're decoding, we still want to pay attention to our inputs. So we're still going to have the cross-attention, the encoder-decoder attention with which we introduced the concept of attention in the first place. So our keys and our values are going to point to our encoder blocks. So we have that component also. And then we still have a feed-forward neural network. This is still a position-wise feed-forward sublayer that, just like the encoder, sort of combines things together for our representations for this particular moment in time. So we have our masked multi-head, big inputs, and then this is a residual connection because we have Y and we have the masked multi-head attention from Y. Both of these are passed through a layer normalization. This forms our first sublayer. Then this sublayer is itself passed through another multi-head attention. This multi-head attention will take this representation from sublayer 1 and it'll pay attention to the inputs. This is the cross-attention component. So we have the heads that pay attention to the encoder over here, spoken loosely. So we have the attention to the encoder layers. And then we take this multi-head output, and then this is passed through our layer norm. We also have the raw outputs from our sublayer 1. And this is also routed directly to our layer normalization. So this is yet another residual connection. We have a layer normalization, and then that layer normalization forms sublayer 2. And then again, the output of sublayer 2 is passed here through a feed-forward neural network that kind of learns to adjust everything for the representation for this particular moment in time. That provides some output, and it has learned weights in there as well. But then we also have another residual connection of the output of sublayer 2 around that feed-forward neural network, and that's passed through a layer norm. So both of these things are passed through a layer norm, and this produces our representation at sublayer 3. So that's essentially it. We have these 3 sublayers. So why do we have these 3 sublayers? So the decoder had 2 sublayers because it had one extra job. The decoder has one extra job compared to the encoder. The encoder just had to represent itself. So I want to have a good representation of my text. But I want to start producing output now. Maybe I want to respond to the user. I want to translate something, whatever the output's going to be. I need to encode myself. I need to represent what I've already produced in context. So I still need to pay attention to myself. So I have the self-attention, which is this first sublayer. Just like the good old RNN, like the multi-input, multi-output RNN, where we have an input sequence and an output sequence, I still want to pay attention to what occurred in the input sequence dynamically. So I have my cross-attention. In fact, I'm going to have multiple heads of cross-attention now, like I mentioned a moment ago. So I can append to different aspects of the inputs. So that's the second layer. So I didn't have to have this cross-attention in the encoder because I was only busy encoding myself at that point. But now I'm decoding, so I have to pay attention to myself and the input. And the feed-forward network basically just like re-encodes things position by position to get me more or less a unique representation for my current token. This is also true of the encoder. So the only thing I'm really adding in the decoder that I didn't have in the encoder is this cross-attention mechanism, which is this second layer over here. So a bit of why this masking that I mentioned earlier. This is a bit of an aside also, but I would still like you to understand sort of the concept of why we're doing this in the first case. During training, you're given entire sentences. You're given the entire French input that you want to translate, and you're given the entire English sentence that you want to output. So you're given je suis étudiant, and you're given I am a student as input and output. Again, these techniques initially were extremely high level and vague and unconstrained. We saw a few examples of how we had to constrain these attention mechanisms. Like before, they didn't care about position; they were agnostic, so we had to make them care about position. So now, an encoder that has access to the entire sequence would be able to look at every single position and kind of cheat, look ahead in its production when it's doing the decoding, when it's producing its output. So if you don't mask the output, like if you're at position T and you want to figure out what word to produce, and you don't want to look ahead, you have to kind of mask out all the positions ahead of you. So in other words, without this mask, position T could attend to position T plus 1, and T plus 2, and T plus 3, and so on, but it hasn't produced them yet, technically. Like as you're speaking, you only produce one word at a time. The same should be true for these models. So the idea is the causal look-ahead mask will set scores to -infinity for all positions j that are bigger than my current position that I'm trying to decode at the moment. So this is the kind of representation here. The penalty is 0 for all positions less than or equal to my current position, but it's -infinity for every position thereafter. So even after a softmax, future positions will have 0 weight. There's no way to attend to them because I've applied applied this maximum penalty to each of those future positions. So when we're doing inference, which we call autoregressive generation, there is no target sequence yet, so the decoder generating one token at a time can still attend to everything it's written in the past, but nothing's been produced yet, like at all. Never mind, cheating on the training set. So the masking trick will be necessary for sure then. This is just a visualization of what we're talking about. When you're in position 0, you can attend to position 0. When you're in position 1, you can attend to position 1 and position 0. When you're in position 3, you can attend to position 0, 1, 2, and 3, and so on. So how this is accomplished is maybe too detailed for the kinds of questions you might receive later on, for those of you who care for such a thing. But I still want you to understand that transformers can technically look at their entire sequences that they're decoding, so we need to ensure when we're training them that they're not mimicking a scenario that wouldn't be possible in real life, where, as you know, time flows in one direction only. This is the visualization that I warned you about. This is from a pretty excellent website here you can click on. It's called the Illustrated Transformer. They kind of have a lot of visualizations. So I'm just going to walk through these very quickly here. We have these words of input, thinking in machines. Each of these are going to be represented as encoded representations for those words. And we add to those the positional encodings. So these could be those sinusoidal, like beautiful looking things we talked about a moment ago, or they could be other forms of like learned representations. So we have an encoder block. So an encoder block, like I mentioned earlier, has 2 sublayers. There's a layer that does self-attention, and then there's a layer norm. And then there's feed-forward neural networks, and then there's a layer norm. And then over here is this kind of dashed dotted line over here represents the residual connection. So I can take the raw output of sublayer 1, the self-attention, and then pass it directly to the normalization layer for the second sublayer, which comes out of these feed-forward neural networks. So the first sublayer is just doing self-attention. The second one, using these feed-forward neural networks, is just kind of adjusting the representations. And then that entire thing is my 2 sublayer encoder block, which is this big green area here. But it's because I'm just pushing matrices and vectors through this network, I can stack them together. And we saw this in earlier modules as well. I can have an arbitrary number of encoders on top of each other here. So I can take the output of my second sublayer of an encoder block and pass it in as a input to yet another encoder block, and so on and so on. So here I only have space for 2 encoder blocks. I mentioned earlier that a lot of these early transformer neural networks by default had a few dozen blocks on top of each other. So you might have 12 or 96 or anywhere in between of these encoder blocks stacked on top of each other. The same high-level stories we tell ourselves about the depth of neural networks usually apply here also. So like a encoder block that is relatively close to the raw inputs will learn aspects of language that are relatively closely related to the words themselves and how maybe like words are nearby each other, relate to one another. But as you go deeper and deeper into this neural network, which is visualized upwards here in this image, you'll learn generally more and more abstract level concepts that might be more closely related to the task, whatever that might be. I mean, that's not always going to be the case. These are often just the stories we tell ourselves, but empirically and through like visualization of what these networks are learning, sometimes that bears out. On the right, we have our decoders. So here in pink here, we have only 1 decoder block that's really visualized. We still have these position encodings that are being attached here at the bottom. So as we're producing our outputs, we're producing an output sequence, which we can attend to. So this self-attention down here, when we're kind of decoding or deciding what word to output, we can pay attention to what I'm thinking right now, and I can also pay attention to what I've previously generated in my particular sequence, so I'm paying attention to myself. The masked normalization occurs here because I don't want to, I haven't produced anything yet, so even if I technically have other text in my training data, I'm ignoring it for now because I want to mimic real life. So I do the masked self-attention. and then that's passed through this normal as layer norm. Now I have the cross attention. So now, because I also want to pay attention to everything in my input, I have cross attention. So that's kind of shown here. This dashed line over here says this is where all the attention to every position in my input comes into play. I incorporate my current representation from the first sublayer. I have a weighted combination of all of the representations from the input sequence, and that is all provided in this cross attention. So I have this encoder-decoder attention, which we called cross attention a moment ago. Again, cross attention and encoder-decoder are the same thing because I'm paying attention across this divide. Again, I have a residual connection, so I have this dashed line basically takes the output of sublayer 1 and passes it to the normalization layer at sublayer 2. So I have that component, and then I have the third sublayer, which is my feedforward neural network, again with residual connections, again passed through this normalization layer. And that's my output for my decoder. And again, I can stack these decoders as many as I want on top of each other, so I don't just need one, I can have many, many of them. But the end of this sequence of decoders being stacked on top of each other, as is usual, I'll slap on a head, usually a linear head, which will basically be a map over the possible words I can produce. I'll write a softmax over that, and then I'll spit out whatever one of these is as the highest value. So, I mean, again, I have a lot of flexibility in producing these things. Not every task will need all of these three components, an encoder or decoder, or any of the subcomponents associated with them. So I can ablate components. Ablation comes from surgery. That basically means removing components of it. So you could take your model, you can remove a part of it, and you can use what is left over to perform some other kind of task. There are a lot of encoder-only variants. This is where I only care about the encoder side of that representation. BERT was a good example of encoder-only models. This can be used for classification, tagging, and embeddings. So if I only care about representing language really well, I might only care about encoding, and then I can take the representations from an encoder and pass those through an arbitrary number of other kinds of classifier to do classification, and it worked really, really well. GPT was really meant for like modeling output in language. Even the very first models of language from the 1940s were based on producing like sampling tokens from a model. So we can throw away the encoder and just start producing outputs. Maybe I prompt the decoder with a little bit of a beginning of a word sequence, so to speak, and then I keep on producing more and more tokens as a decoder-only model. The GPT series follows that approach. And then the encoder and decoder model is both of them together. This is useful for sequence-to-sequence modeling, translation, summarization, QA. As we've seen, a lot of these decoder-only models perform really, really well without having to do encoding first. So the principle generally is if you want to understand a sequence, encoder-only should be used. If you want to generate outputs like in a chatbot, you might use decoding. And if you want to map one sequence to another, you might use encoder-decoder. But just like so many other things in machine learning, you should do the experiment yourself because sometimes you might get a really good performance using something that's a lot simpler. This is similar in some sense to the difference between a prior distribution and a posterior distribution. So sometimes I like thinking of an encoder model as like learning the prior of something. It's obviously not the case. It's more complicated than that by a large extent, but it's sort of like this is the prior representation of the language. And the decoder is sort of like, well, if I have this input, I want to produce that output. That's sort of the noisy channel, the probability of y given x. And then the entire thing, the probability of x and y together is the encoder, decoder together. The probability of x and y is the probability of x, which is encoded, times the probability of y given x, which we get from the decoder. And like we saw in discriminative classification, sometimes you don't need to learn the priors in order to get good discriminative capacity. As a bit of a side note, you can ignore what I just said a moment ago, but I find that to be a little bit interesting.